Okay, this is my thesis presentation. My thesis focused on the development and implementation of a hybrid electric vehicle control strategy. My name is Matthieu Orr, and I graduated from McMaster University in 2021 with a Bachelor's of Mechanical Engineering. I was a part of the McMaster Engineering EcoCar team for 4 years, and this is where I conducted all my research. So, what is the EcoCar project? The EcoCar project is sponsored by General Motors, and the goal is to convert a 2019 Chevrolet Blazer from full gasoline vehicle into a hybrid electric vehicle. What type of hybrid did we design? We designed a non-plug-in P4 parallel through-the-road hybrid. This is a four-wheel drive hybrid where the front and the rear axles are connected through the road and not by a drivetrain. The front wheels are engine powered and the rear wheels are electric motor powered. The electric motor is also responsible for charging the high voltage battery with regen braking. So what does it take to convert a Chevrolet Blazer from a gas powered vehicle to a hybrid electric vehicle? Over the 4 years of the EcoCar competition, we designed all the packaging for the new components into the Chevrolet Blazer. We developed a mathematical model for the Chevrolet Blazer and all its components. Once the Chevrolet Blazer arrived at the Mark building, we stripped it of all its components. We took out the engine, the transmission, all the drive shafts, and we took out the stock fuel tank. We then tested every component that we were going to put into the Blazer on a test bench. Once every component had been tested, we then integrated these components into the Blazer. Once in the Blazer, they were tested again. We put the vehicle on a chassis dynamometer to do even more testing, where we established control of the engine. We worked with the clutch in our rear. Once the dyno testing was complete, the Mac Team vehicle was able to be driven on public roads. The Mac Team vehicle accumulated over 1,500 kilometers of public road driving. Over the 4 years of the EcoCar competition, what was my contribution to the team and what was my contribution to this thesis? I was responsible for maintaining the mathematical model for the McMaster vehicle. I ran the YASA bench testing. I ran the dyno testing. I was a part of the BAS testing and the battery testing. But once all the components were integrated into the vehicle, it was my responsibility to make all the components work together. But once all the components were working together, the real project started. The torque split control strategy. The torque split control strategy, the idea was birthed in the model way back in the first year of the EcoCar competition. The idea is to have the engine operate at its most efficient point as often as humanly possible throughout a drive cycle. We were provided with the engine's optimal efficiency line, and this line represents the most efficient torque output of the engine at a given speed of the engine. And throughout a drive cycle, we want to operate along this line as often as possible. The most important rule that must be followed for this torque split strategy is that the driver request must always be fulfilled no matter what. And so we always try to operate along the optimal efficiency line, but the driver request comes first. So if the driver request is on the optimal efficiency line, great, that's where the engine will operate. If it's below the efficiency line, that's also where the engine will operate. A little less efficient, but that's what we have to do. If the driver request is above the optimal efficiency line and within the operating points of the electric motor, the engine will operate at the optimal efficiency line, and then the motor will make up the difference to get to the driver request. And this is how we keep our engine on the optimal efficiency line as often as possible. If the driver request is significantly above the optimal efficiency line, then again, the driver request must be fulfilled. So a combination of the electric motor and the engine will operate to get to that point. So that explains our goal of operating along the engine's optimal efficiency line as often as possible. Now, if our battery had infinite electricity, we would be able to operate along that point as often as we possibly can. It would happen all the time. But we don't have infinite electricity. And because we are a non-plug-in hybrid, we can only regenerative brake through our electric motor to charge our high voltage battery. So because of our non-plug-in limitations, our vehicle needs to maintain charge sustaining throughout a drive cycle, meaning we can't end a drive cycle significantly lower on state of charge than when we begin, so that every time we start our vehicle, we're able to drive regularly. If we always lost charge over time, eventually our battery would fully die and there's nothing we can do because we can't plug it in. So charge sustaining is essential for the operation of this vehicle. So how does the charge sustaining considerations affect our optimal efficiency line torque split strategy? Simple. A motor penalty value is determined based on our target state of charge, which is 50%, and our current state of charge, which let's say is 40%. And at a 40% charge, what happens is our optimal efficiency line is artificially raised, thus increasing our engine's output torque and lowering our electric motor's output torque. So as you look at this graph, for example, in a world where our motor penalty is high, our optimal efficiency line might increase all the way to the top of that red line. It might get all the way to that green point, and in a world where that has happened to our optimal efficiency line, our motor would output zero torque, even though if at the 50% mark, it would output torque. So this effectively reduces our electric motor output, thus we actually regen more throughout a drive cycle. Because the regenerative braking throughout a drive cycle is unaffected by this charge sustaining algorithm and equation. So our regen braking throughout a drive cycle is very consistent. So just by lowering our electric motor output throughout a drive cycle, we then get net gains on our regenerative braking. So there's the idea. Now, did it work? Absolutely a little bit. Throughout on-road testing, we always drove on one drive cycle. We called it the McMaster drive cycle through Hamilton, and we get dense downtown driving and highway driving and suburban driving. So the first question is our vehicle charge sustaining? Because if not, our vehicle won't really work at all. And here's a picture of a long hybrid drive cycle where we did 9 full McMaster drive cycles in a row. It's so long that we had to cut it into 2 can logs. And you can see the voltage, the steady state voltage of our battery doing I wouldn't call it a sinusoidal wave, but it is bouncing back up whenever we dip too low. And this shows that we clearly are charge sustaining, which is great. Now the question is, how efficient are we? Not very efficient at all, as it turns out. Although we do have improvements over engine-only operation. I mean, we would hope that would happen. When we drive engine-only, our fuel efficiency is 18.2 miles per gallon. And when we drive in hybrid operation, our fuel efficiency is 19.2 miles per gallon, which is only a 5.5% increase in fuel efficiency, and 19.2 miles per gallon is also very not good. So the real question is, why such a low fuel efficiency? Let's investigate. Okay, so let's have a look at our engine operating points for our engine-only drive cycle and a hybrid drive cycle. As you can see, on the right, that is our hybrid drive cycle. All the red dots are engine operating points when the motor is also operating. And as you can see, there's a green line going through there, and that is our engine's optimal efficiency line. And as you can see, we would like those red dots to be along that line, and clearly they are not along that line. Another key thing to note is that our maximum engine operating points are in that red line, and as you can see in the engine-only drive cycle, there really aren't that many points that operate on that line. There are a few, but not a crazy amount. Whereas in our hybrid drive cycle, we operate along that maximum line a lot. And so this is evidence, or this is a potential place we can improve to increase our fuel efficiency, because an engine operating at its maximum is not an efficient engine. And so if we are able to determine why this is happening, we can then improve.